So you were telling me this, first column of S, second column of S, just flip these.
So for R, you could choose either eigenvalue.
Yes.
No.
Yeah, let's do one more. This is interesting. Oh no, actually, hold on. It's too easy. Yeah. I'm going to call this good. What do you guys think?
You can call it question. And for S, you have to make sure you use, to build S, you have to use the corresponding eigenvector.
Absolutely right.
Okay.
But let me just, I think what you're getting at, so I can clarify it, is let's say we use this eigenvalue and eigenvector pair. Let's split this up into 2, 1 plus I times negative 1, 0. So what's the first column of R, if I do it this way? 1, negative 1. Given that R is a rotation scaling matrix, first column is AB, second column is negative BA. What's the second column here? And then, what's the S matrix if I base it on this one? First column? Second column? Okay, this last part isn't in the book. But it seems like a good way to end the course. Start with an example about why we care about this. General theory. And I realize you do want a text or you want something written about this. So in that handout that I gave you in the first day of class, I gave you a field manual for diagonalization, and it walks through the steps. So I'm going to introduce this part about why we care about this. I'll work through the example, and there's a written example in that handout. There's a lot of notes in the handout. I'm going to use this matrix. Subtract lambda from the diagonal. Copy all that over. This is me doing some algebra. I set it up. We've been doing it for a couple of weeks now. And then I did some algebra 1. We've been doing for most of your life. So what are the eigenvalues? So 3 and 3. I'm going to do this for lambda equals 3. X plus 1 plus 3x. Same equation, which I'm expecting. So can you give me an x and a y that work?
1.
1, The only thing I wouldn't have accepted was 0, 0. Anything else that works is good. So 1, 1. And then let's do this for the other eigenvalue, lambda equals 3. -1, -1. Sure. Get that. What's your D? First column of S. And then what's promised? So I can factor the A. My matrix I have over there is S times D times S inverse. So what's S inverse? Doesn't work, exactly. Okay, so the problem is, this is essentially the same as that, right? So, I don't know what to do if the same eigenvalue shows up twice. So let's go back a little bit. If I have a generic 2 by 2 matrix, that is A, B, C, D. And I do the crisscross, is I'm going to get an equation that looks like this. And when I use the quadratic formula, I'm going to get this. And the first couple examples that we did was this b squared minus 4ac was positive, which means that I'm calculating the eigenvalues. I get negative b plus that number and negative b minus that number. And then the examples that we started yesterday, or I started Wednesday, and continue today, is this b squared minus 4ac is a negative number. When it's a negative number, that gives us the imaginary ones. So if b squared minus 4ac is positive, you know what to do. If b squared minus 4ac is negative, you know what to do. But what's the missing case? 0. Zero, exactly. So if it's 0, that means that your numerators look like negative b plus square root of 0 and negative b minus the square root of 0, which are the same number. When you factored this, I erased it already, you get the same number twice. So when you get the same number twice, it's our trick for diagonalization doesn't work. So the last part of the course is what do? How do you factor the matrix into something nice when you can't do the SDS inverse? Brief summary of the long journey is when we're calculating eigenvalues, that b squared minus 4ac positive means we can factor this into an SD S inverse. And the nice thing about the D was it was diagonal. And we could do an SDS inverse in this case, but we have a lot of imaginary numbers to deal with. Instead, a nicer way to do it is to factor it into an SR S inverse. And what was the nice structural property of the R? Did these all have real numbers in it? And what kind of matrix was the R? It was a rotation and scaling matrix. So we also In this case, we call that middle matrix J. And I'll show you what J looks like. Oops. So the J matrix looks like this. It's almost a diagonal matrix. And the only difference is it's going to have a 1 up here rather than 0. So you wanted this to be the D matrix, but that didn't quite work out. So there's a mathematician named Jordan, a French mathematician, who said, the closest that we can do is replace this 0 by a 1, and then we'll call it J. So we're going to talk a little bit about that. That's basic. Just so we're clear on this example I just did. I had that matrix, and I got the characteristic